This module is an introduction to module 3. This video is an introduction to module 3, that is introduction to the beam element and derivation of the stiffness matrix for the beam element. In this video you shall see about the derivation for the beam element, stiffness matrix for the beam element, and the different types of beams, what do we mean by beams, and introduction to the beam element is covered in this video. So this video deals with the beam element that is used for the finite element analysis of beam elements that represent a beam type of structure. So beams play a very significant roles in engineering applications, including buildings, bridges, in automobiles, and in airplane structures. So how do we define a beam? A beam is defined as a long, slender structural member whose cross-sectional dimension is relatively smaller when compared to its length. So literally speaking, the length will be huge or higher when compared to its cross-sectional area. The cross-sectional area will be negligible. So beams are commonly subjected to transverse types of loading and they produce significant bending moment. The deformed shape of a beam is described by transverse displacement, that is vertical deflection, and rotation. So transverse displacement is considered as vertical deflection and rotation of a beam is considered as slope of the beam. So the vertical deflection and rotations are considered as the two unknown degrees of freedom at each of the node of the beam element. So the two degrees of freedom for a beam element is the transverse displacement or the vertical deflection and slope or rotation of the beam element. So mathematically, if we are seeing, the main difference between a beam element and the bar element is the increased order of continuity required for the assumed transverse displacement field that has to be continuous, and it should possess a continuous first derivative along the x-axis. So in order to meet this requirement, both deflection and slopes are considered as the nodal degrees of freedom for a beam element. So the primary tool for analysis of the beam element is Euler-Bernoulli beam equation. So we shall see this in the next slide. So the primary tool for analysis of a beam element is the Euler-Bernoulli beam equation. Other methods for determining the deflection of the beam include slope deflection method of virtual work, or some of the other methods. For calculation of internal forces of a beam, we have moment distribution method, force or flexibility method, and stiffness method. However, all these methods have their own limitations. That is, if either of geometry, loading, material properties, or boundary conditions become arbitrary in nature. So finite element techniques can handle such cases and relieves the analyzer of making simplifications to arrive at approximate solutions. As discussed, beam is a long structural member which is supported along the length and subjected to external forces or loads that are acting transversely, that is perpendicular to the center line. Beam is sufficiently long when compared to its lateral dimensions or its cross-sectional area. So the length of beam is quite huge. There are many types of beams. Some of them are explained or given here. That is, we have cantilever beam. One end it is supported, one end is free. Simply supported beam. There is a support at the bottom of the beam and it allows horizontal movement. Vertical movement is not allowed. Overhanging beams, fixed beam, continuous beam. So these are some of the examples. We will see in the next slides with the diagram what do we mean by a cantilever beam, what do we mean by a simply supported beam, what do we mean by a overhanging beam, and what do we mean by a fixed beam and a continuous beam. We shall see in the next slide with the diagrammatic representation. There it will be very clear. Okay, so here you can see a cantilever beam. It is a beam with one end free and one end fixed. Hence it is called as a cantilever beam. A simply supported beam, a beam supported or resting freely on the supports at its both ends. It is called as a simply supported beam. A beam that is supported or resting freely on the supports at both the ends is called as a simply supported beam. An overhanging beam is one for both the end portions are extended beyond the support. You can see in the diagram a overhanging beam is shown. So at A and B you have supports, whereas C is protruding outside. So this is an example for a overhanging beam. So beyond the support B it is still running, but there is no support at point C. It is just freely hanging. Fixed beam. So fixed beam at both ends it is fixed. For example, a beam that is built into the walls, it is called as fixed beam. It cannot move at both the ends. There is no free movement at both the ends. A continuous beam, a beam which has more than two supports, is called as a continuous beam. So a continuous beam will have a multiple support. Continuous beams will have multiple supports. So transverse loading on beams. A load which is acting vertically downward on the horizontal beam is called transverse load. A load that is acting vertically downward on horizontal beam is called as a transverse load. So types of transverse loads. We have a point load or concentrated load. So it acts at a particular point and it is called as a point load. A load that acts at one particular point in the entire stretch of the beam is called as a point load. Uniformly distributed load. So this load is spread over the beam in such a manner that the rate of loading is uniform throughout its length. So weight, it is represented as W per unit length. So the load is spread over beam in such a manner that the rate of loading is uniform throughout the length. Next, uniformly varying load. So a load which is spread over the beam in such a manner that the rate of loading is uniformly varying from one point to another point along the length of the beam. So the load is 0 at one end and increases uniformly at the other end. It is also called as a triangular load. It is also called as a triangular load. Short form of this is UVL, uniformly varying load. You can see in the diagram at point A it is almost 0, and at point B it has a value, and this value increases uniformly from point A to point B. It is uniformly increasing. Okay, as seen in the previous slides, we have tried to understand the beam element, various types of beams and the parameters that define the beam element. So now on we will try to derive the equation for the beam element. So coming to the topic, a beam element is considered to be a long structural member with relatively smaller cross-sectional dimension or cross-sectional area, and it is generally subjected to bending moment due to transverse forces, and these transverse forces will be acting on it, which will induce the bending moment. So the deformed shape of a beam is described by the transverse displacement and rotation of the beam or the slope of the beam element. So the transverse displacement and rotation at each end of the beam element is treated as the unknown degree of freedom. So we will have 2 degrees of freedom at each node. So for one beam element there will be 4 degrees of freedom. So transverse displacement will be 1 degree of freedom and rotation will be 1 degree of freedom. So each beam will have 2 nodes and hence 4 degrees of freedom. 2 at each node will be present. So let us consider a beam which is shown in the figure below, and it is considered to have 2 nodes, node 1 on the left hand side and node 2 at the right hand side, and each node has a 2 degrees of freedom, that is mu1 and theta 1 at node 1 and mu2 and theta 2 at the node 2. So there are totally 4 degrees of freedom for a 2 noded beam element. So for a beam element with the 2 nodes there will be 4 degrees of freedom, 2 each at one node. So let us assume a cubic polynomial displacement model for mu x. So mu x will be equal to, mu x is nothing but a function of x will be equal to a0 plus a1x plus a2x square plus a3x cube. So this is a cubic polynomial displacement function. So a polynomial displacement function, there will be 4 constants and 3 third power to the variable x. So a0, a1, a2 and a3 are the generalized coordinates that are required to be determined using the boundary conditions or the nodal conditions. So at the point when x is equal to 0, mu x or the function of x will be mu1, and the differential of x with respect to x will be theta 1. So at x is equal to 0, mu x is equal to mu1 and del of mu x by del x is equal to theta 1. Similarly, when x is equal to L, mu x is mu2 because it is at node 2, and mu and del mu x by del x is equal to theta 2, that is slope at node 2. Now equation can be represented as mu is equal to h into q, where h is equal to h1 le by 2 into h2, h3 le by 2 into h4. So this equation 2 is the Hermite shape function and is nodal displacement, q is the nodal displacement vector. So h is the Hermite shape function and q is the nodal displacement vector. So q is mu1 theta 1 mu2 and theta 2, or mu1 theta 2 mu3 theta 4. So it is the displacement vector at node 1 and node 2. So this is the diagrammatic representation of the beam element that is subjected to the load, and it shows the slope at any particular part of the beam element. You can clearly see the diagrammatic representation of the beam element with the slope and the nodal functions. So next we shall see the stiffness matrix for the beam element. So the stiffness matrix is derived by using a direct equilibrium approach and beam theory sign conventions. So we know that the transverse displacement is given by the formula mu of x is equal to 2 by L cube del 1y minus del 2y plus 1 by L square phi 1 plus phi 2 into x cube plus minus 3 by L square into d1y minus d2y minus 1 by L 2 phi 1 plus phi 2 into x square plus phi 1 x plus d1y. So this is the transverse displacement equation mu of x or function of x. Now if I am finding the first differential of this value mu of x, I have to differentiate this equation with respect to x. I'll write it as del of mu of x by dx is equal to 3x square into the constant term, that is 2 by L cube into d1y minus d2y plus 1 by L square into phi 1 plus phi 2 plus 2 into x into the again the constant term minus 3 by L square into d1y minus d2y minus 1 by L into 2 phi 1 plus phi 2 plus phi 1, because the x term vanishes here to when we are differentiating it, and the constant term vanishes, so plus d1y is not shown here. Now if I want to find the second differential, that is del square mu of x by dx square, I have to further differentiate this. So I'll get this equation to be 6x into the constant term 2 by L cube into d1y minus d2y plus 1 by L square into phi 1 plus phi 2 plus 2 into minus 3 by L square d1y minus d2y minus 1 by L into 2 phi 1 plus phi 2, and the constant term phi 1 vanishes here. So again, if I am finding the third differential, d cube of mu of x by dx cube, then only the first term will remain, that is 6 into x will vanish, 6 into 2 by L cube into d1y minus d2y plus 1 by L square into phi 1 plus phi 2, and the second term, that is a constant, will vanish. Now moving on to the next slide. Let me put x is equal to 0 in the equation 2.113, that is the last equation of the previous slide. So when I put the value of x is equal to 0, del square mu of x by dx square will be equal to 0 plus 2 into minus 3 by L square into d1y minus d2y minus 1 by L into 2 phi 1 plus phi 2 minus, so now on further simplification I will take the term 2 inside and multiply it. So 2 into 3 becomes 6, so minus 6 by L square into d1y minus d2y minus 2 by L into 2 phi 1 plus phi 2. So I can further rewrite it as 1 by L cube into minus 6L d1y plus 6L d2y minus 4L square phi 1 minus 2L square phi 2. So the term 1 by L cube, I am taking it common outside, and inside I am adding multiplying the L term wherever it is not available. So this equation will be 2.115. So del square mu of 0 by dx square is equal to 1 by L cube into minus 6L d1y minus 4L square phi 1 plus 6L d2y minus 2L square phi 2. So this video deals with the beam element that is used for the finite element analysis of beam elements that represent a beam type of structure. So beams play a very significant roles in engineering applications, including buildings, bridges, in automobiles, and in airplane structures. So how do we define a beam? A beam is defined as a long, slender structural member whose cross-sectional dimension is relatively smaller when compared to its length. So literally speaking, the length will be huge or higher when compared to its cross-sectional area. The cross-sectional area will be negligible. So beams are commonly subjected to transverse types of loading, and they produce significant bending moment. The deformed shape of a beam is described by transverse displacement, that is vertical deflection, and rotation. So transverse displacement is considered as vertical deflection, and rotation of a beam is considered as slope of the beam. So the vertical deflection and rotations are considered as the two unknown degrees of freedom at each of the node of the beam element. So the two degrees of freedom for a beam element is the transverse displacement or the vertical deflection, and slope or rotation of the beam element. So mathematically, if we are seeing, the main difference between a beam element and the bar element is the increased order of continuity. So when I put x is equal to 0 in the equation 2.114, I will get d cube of mu of 0 by dx cube is equal to 6 into 2 by L cube into d1y minus d2y plus 1 by L square into phi 1 plus phi 2, that is equal to 1 by L cube into 12 d1y minus 12 d2y plus 6 L phi 1 plus 6 L phi 2. So which is further equal to d cube of mu of x by dx cube is equal to 1 by L cube into 12 d1y plus 6 L phi 1 minus 12 d2y plus 6 L phi 2. So this is equation 2.117. So if I further put x is equal to L in the equation 2.114, I can rewrite the equation as del cube of mu of L by dx cube is equal to 6 into 2 by L cube into d1y minus d2y plus 1 by L square into phi 1 plus phi 2, which I can further rewrite as 1 by L cube into 12 d1y minus 12 d2y plus 6L phi 1 plus 6L phi 2. So this will be further reduced as per the equation 2.118 and will be rewritten as del cube of mu of L divided by del x cube is equal to 1 by L cube into 12 d1y plus 6L phi 1 minus 12 d2y plus 6L phi 2. So we know that nodal force F of 1y is equal to EI into d cube mu of x by dx cube. So F of 1y is equal to EI by L cube into 12 d1y plus 6L phi 1 minus 12 d2y plus 6L phi 2. So from the equation 2.117 I have deduced this. So if I am finding out the bending moment m1, it is nothing but equal to minus EI into del square mu of 0 by dx square. So I will substitute the equation for del square mu of 0 by dx square in this equation, and I will rewrite it as m1 is equal to EI by L cube into 6L d1y plus 4L square phi 1 minus 6L d2y plus 2L square phi 2. So this I have derived from equation 2.115. So the nodal forces F of 2y is equal to minus EI into d cube mu of L divided by dx cube. So from equation 2.118 I can rewrite it as minus EI by L cube into 12 d1y plus 6L phi 1 minus 12 d2y plus 6L phi 2. So F of 2y is equal to EI by L cube into minus 12 d1y minus 6L phi 1 plus 12 d2y minus 6L phi 2. So the bending moment I can write it as m suffix 2 is equal to EI into d square mu of L by dx square. So m2 bending moment at node 2 will be EI by L cube into 6L d1y plus 2L square phi 1 minus 6L d2y plus 4L square phi 2. So this is deduced from equation 2.116. Now in order to write the value of f of 1y, m1, f of 2y and m2 in the matrix form, I can rearrange and write all these terms in the matrix form. So we shall see this in the next slide. So arranging the above equation f of 1y, m1, f2y, m2 in the matrix form, I can rewrite it as f of 1y, m1, f of 2y, m2 is equal to EI by L cube. So EI by L is common throughout. So EI by L cube into 12 6L minus 12 6L 6L 4L square minus 6L 2L square minus 12 minus 6L 12 minus 6L 6L 2L square minus 6L 4L square into d1y phi 1 d2y phi 2. So this is the finite element equation for a beam element. So the left hand side shows the force terms, the right hand side shows the stiffness matrix EI by L cube into 12 6L minus 12 6L 6L 4L square minus 6L 2L square minus 12 minus 6L 12 minus 6L 6L 2L square minus 6L 4L square is the stiffness matrix for the beam element, and the term d1y phi 1 d2y phi 2 is nothing but the displacement vector. So for a given beam element, if the modulus of elasticity E, Young's modulus of elasticity or Young's modulus E is known, moment of inertia I is known, and the length of the beam element is known, we can derive the stiffness matrix and then solve the beam element for the calculation of the force vectors and the displacement vectors. So this is the derivation for the stiffness matrix of the beam element. So you are expected to remember this stiffness matrix. You are expected to remember this stiffness matrix while solving the problems.